Okay, so what we're discussing right now is about the the AI projects. We have already finalized 2 projects. The first one is machine learning project. It's going to be the same project for 2 groups. The only difference that groups may choose different algorithms for classification. I'm going to come back to this project. Otherwise, for the other project, which is a deep learning project, so the idea is to start with 1 research paper. This is the first one. We may see more than 1 paper, so it depends on the speed and time. So the first step is to start reading this work and understanding this research paper. So what I expect from you is a presentation about what you understood from this paper. For the second group, it's going to be first and second groups. Is going to be classification with typical machine learning algorithms, where we have mainly 3 to 4 data sets in the start. MNIST data, which is digit data sets, so everyone's going to use and apply a machine learning algorithm. Then we chosen to make some to specialize, let me say, in a particular domain, where we found the skin cancer case, one of the important use cases. So here we suggested 2 data sets, classification in order to have fair comparison with the MNIST, so it's better to be grayscale. So first step is that you are going to transform your data or images into grayscale. And so what you have in the case of skin cancer, 2 data sets. The first one is called the HAM10K, which is similar to MNIST in the case of skin cancer, which means that if you have a machine learning model, you can use this one first to validate your model. The only thing, I'm keeping the link from Kaggle where you can download this data set and have more details about this data set. But the only thing that I can mention at this context is that this data set is unbalanced, which is a big problem for now. So you need to use some techniques to have a balanced version from this data. Otherwise, I'm providing you with another data set, which is the DEN T2M, which is balanced data, clean data, and just you need to run your algorithm on this. The difference between both data sets is that one is binary, means we have 2 classes, and for the other case, we have multi-class classification. So here you may compare your models based on 2 different cases. There is also the option once your model is running, there is a data set which is in a different context, the biomedical context, which is the HEP to cells. This data set, you can run it. It's a clean data set, balanced one, and there is no problems with this data set as well. So the only challenging one may be the HAM. So here one of the tips is that you come back to the state of the art, try to see what other people did with this data, and based on your performance, you keep checking if whatever techniques you are using are good or not. Any other data set or any other comparison with another field or domain is also welcome. So for the first step, just to limit the work, and we are going to have a comparison between different ML algorithms. In the feature extraction step, we are going to use a defined feature extractor, which is the scale and variant feature transform. Only we are going to extract the key points from an image, and that key points are going to be fed into your machine learning algorithm. Here, both groups can choose whether KNN we seen last time, SVM we are seeing today, random forest decision trees, XGBoost algorithms that we are going to see, and CNN as well. So you will choose one of these algorithms, but the CNN algorithm is always there as a must. So it's must, there is no choice. The only thing here, I want those students who choose an ML project to compare with deep learning approaches. So this is why I am keeping this one. So you can compare your results. I can expect some students are going to, from both groups, are going to work on SVM. So I have no problem to have collaboration between both groups. For example, here I have Farah from group 1, I have Ayub from group 2. If it's happening that Farah and Ayub are both working on SVM, you can work together, I have no problem. Perhaps one of the reasons of keeping the same projects to collaborate even between the groups. So this is the first thing. The second thing now is the output for this project is going to be a detailed comparison between machine learning algorithms in a given context that is dependent upon from the data. So that is it. This is, so the first evaluation is, as I was mentioning last time, is expected for 11 November. And any question like for this point?
So what's due by the first evaluation?
Okay, let's go back now to the syllabus, what we have here. Okay, so 16 October, we were launching the project and you guys were supposed to start working like since that time, but unfortunately until today, the groups are not working. So I may consider this as a technical problem. I hope you guys are going to solve. Until 11 November, we still have time. We still like have, let's say 2 weeks to understand data because, so I'm going to divide the project into like 3 phases. The way to divide the project is different from ML to the research paper. So what I will expect for 11 November from the advanced deep learning group is just a presentation and their understanding to that paper I'm giving for reading. From the machine learning group, what I expect is like a first draft, okay, of notebooks where you guys are presenting your business understanding. Business understanding means in the context of MNIST, how you were visualizing, like uploading your data, reading that. Like I will show you an example, okay? Presenting the correlation like between classes, plotting how many classes, checking if there is any problems, if data is balanced, okay? If not, what like techniques are you using to get rid from this problem? So for me, until 11, I don't expect you are running any ML algorithm. Until 11, if you are going to read your data, that would be more than enough, okay? Read and understand and fix if there are any like issues. Next, the second validation here, I may expect a code running for everyone. So second validation is going to be by the end of like the semester, let's say for now, 2nd December. And from first to second validation here, we are going to be having meetings, like if you want during my office hours, or if you want like at the end of each like class, we may have 15 minutes for the first group, 15 minutes for the second group. If you have questions or problems, we can discuss that together. So what will happen for the first validation is that you guys, like group 1 is going to be there, present their work. Everyone must attend the validation because like you are going to have marks for the first validation. If you really understood, upload your data, did your job. So this is part of the evaluation, let's say 30%. Then another 30% probably will be for the second validation when you are having your code running. And the third validation now is a final exam where you are going to present your whole project, where you are going to provide a GitHub link for your code. You are going to present it for someone, like if someone is not the expert of ML and like you are selling your solution, to show him like we did comparison, this is the best algorithm, we recommend going for this algorithm, we are using, for example, this and this and this metric, and it's showing this, and based on these statistics, in this case, we go, if you are working, for example, for the skin cancer, for example, you are going to use the CNN. For biomedical data, you are going to use SVM. Don't consider my words, okay? But something like this, like a final decision from your whole project, and you're going to present it like as output, the whole thing, coding, like why? Interpretation of the results, not like you're going to bring a table and say, okay, CNN is giving 100%, SVM is giving 90%, CNN is better, bye-bye. No, you need to say, for example, why the limitation for this algorithm, why this algorithm is giving better results. So I may also evaluate your deep understanding for each of the algorithms, things that we are doing already in the class. Okay? So.
Makes sense, thank you.
So welcome. Validations are, all group members must be there. They must have their presentation. It's like finishing the first step, then second step towards the last step. This is how it works. So for the first group, I think it's clear, first and second machine learning groups. For the second presentation now for the deep learning group. Here also I'm expecting some code. So we may have another meeting in the middle. So where we will discuss what you did. I can provide you with some code and we can add the innovation part if things are working well. And so it depends all from your work. So if you guys are working hard, I will be working with you. If you guys are not really working hard, so I cannot give you more and this may bother you. So it depends on you in all cases. And at the end, the final project exam is going to be also a presentation, as I was mentioning, for all groups, what you did from the start, a brief understanding of the paper, what were the problems, how you are trying to code that, what you did as an innovation part for that, and that is it, okay? So it's like hands-on thing because this class is an AI class. It's not machine learning class. It's not deep learning class. But in AI, the main thing is machine learning, deep learning. So this is why we've chosen the projects for machine learning, deep learning. And I'm sure not all the students are taking machine learning class. Not all the students are taking deep learning class. So the thing is to start your first hands-on experience. You can see that the project is not hard at all, but just to expose you for the first time to coding, to understanding, to comparison of algorithms, and that is it. So I think that is it. And any other questions? Okay, now what we have for today, I may start quickly with...
Actually, sorry, I have one more.
Yeah, sure.
So when we look at our exam, under grades, like it shows a grade, but not like an official one. Is that grade there final now? Like, is that our grade for that exam?
No, it's still not the final grading that is showing there, if you can see something.
Okay. Phew,
Yeah.
scared.
It's not the final one. I think that is due to the I'm already correcting the biggest parts. I'm considering like the algorithms and all that is done for all the students. Still few questions. So if you have now A star, A or A plus, it may increase because still I'm not grading everything. Simple questions are still there, so it's going to be increasing. Farah, for you also you can see, or Ayub, this. I don't know. I was mentioning that it's not published yet, the results for everyone. I cannot share it now because we're in a meeting, but I think you cannot see that, right?
Yesterday it showed like 50% or something, and I was freaking out a little bit. So that's why I was
No.
curious.
It's not the final. I was mentioning
It's 23.
no, it's not the final one. It's not the final one. Only for those students who sent me an email, I'm done with the pass with the last questions. Otherwise, for you, it's not the final one. Ayub is 65 for you? No, it's showing. I think I'll stop sharing the check.
74.
Which is, I think, until now. I'm not sure if it's updated for everyone, so let's keep it not final, okay? Only once.
Professor,
Yeah.
I have a quick question here on Zoom. I was just wondering, did you say that there's another quiz up or test up on Canvas? Because I don't have one on my Canvas, if I heard that right.
Yes, the second exam is there, but the thing is that for now we are not having a second exam because
Okay.
the main idea or strategy from having an exam is to evaluate your knowledge. So for me, I am evaluating for the first exam your knowledge on AI, simple problem solving and gaming and all that. For the second exam, my plan is to evaluate if you are getting the concepts of machine learning algorithms right or not. So it's going to be a simple quiz. You can expect that like within the upcoming 2 weeks, okay? It will be a very simple quiz, but it's not yet there. I think we are today going to go through the SVM, then we need to finish the ensemblist methods, and after that we'll have the exam because it's covering this part of learning, okay?
Yep. Thank you so much, Professor. I appreciate it.
Okay, welcome. So for the exam here, it will be just theoretical knowledge that before you are starting your project and going through the validations, you are like getting the concepts. You know what is KNN, you know what means SVM, you know when to apply k-means, when to go for the Gaussian mixture, for example. So you distinguish between these concepts, just theoretical knowledge. Coding and hands-on experience, this is going to be evaluated for the project. So that is it. Now what we have next, any other questions? Okay, I think we are done with the questions. Now, last time what we did? Last time, we're discussing discriminative methods, including the KNN algorithm. And we say the KNN algorithm is an algorithm like designed for classification purpose. We can predict like exact values using the KNN, but mainly we use it for classification. One simple example, if like we see that someone bought one flower, in the next like purchase, what kind of flower he's going to buy based on the current like flower he chosen. So for this, we were saying that we need to compute like to check the similarity. So basically he's going to buy something quite similar from what he bought last time. So we checked the most near or the nearest flowers from the flower he's already buying. So this is the idea of KNN. And next, so we had this illustration with points. Now I have like my points, and I have a new point here. What I don't understand if it belongs to the orange or green class. The idea is that how to guess. If I consider KNN, I have my parameter K, so I need to fix it. I'm going to decide this new sample coming if it's orange or blue based on one nearest neighbor. So the nearest one is orange, so I may decide in this case that it's orange. However, we've seen that if you see the whole like set of elements here, mainly they are not orange. So the orange element is here by luck or bad luck as an outlier. And if the outlier is near to my new sample, this is going to impact my decision, okay? So in this case, we use a larger number of K, we increment. So I'm going to consider 2 cases, 3 cases, 3 neighbors, 2 neighbors, 4 neighbors, and I'm going to decide based on the majority. So this node is more, the nearest points to this node are blue, 3 are blue, 1 is orange. So mainly this point is predicted to be a blue one, which is fair. Okay, we see that this algorithm has a set of advantages, disadvantages, and we were discussing all this. Now what I did, I was sharing with you, and you find that in what we say in the modules section, like always, you will find this notebook where I am going to go quickly through this. I was discussing it last time, and we said that if we are working with machine learning could fit whatever your context. So if you are working with medical, you can use it. If you are working with cybersecurity, you can use it. If you are working with, I don't know, with the police, with transportation, with insecurity context or whatever, so you can still use machine learning algorithm. So the use of the machine learning, which is the technology or the algorithm you are going to choose for classifying. So the classification task depends on the data. If you are classifying flowers, if you can like classify networks like connections, you can classify like people with disease, or it depends on the context. So last time when we were discussing this, we said that so the KNN algorithm depends, or whatever machine learning algorithm depends upon from the context. So one of the contexts I was discussing when one of the students was how to use machine learning in cybersecurity. For this, I'm bringing this lab. So this lab is supposed to take more time if you are taking a machine learning class, but my only purpose in this AI class is just to show you how we can like use it for a particular context. So for this context, which is a cybersecurity context, you can guess how we are using like our KNN algorithm. So here our task is to build a network intrusion detector. And in this case, so what we are going to classify, if we have a new connection, we are going to distinguish between bad connections, means an attack in this case, or good, which is a normal connection. Okay, so this is your data. In this context, you may find available on the net data sets, and this is what you use is called KDD data set. I'm already like uploading this on the same section. And first thing, after reading your data, you need to understand it. So for the data, if you want to see, so this is a real world simulation of some data, like it's a simulation of the typical US Air Force LAN. So just when we say about simulation, so most of the cases we do this because we do not have access to the real configuration or settings. So simulation is something like a similar context, but like if we are having results, mainly if we're going to apply in the real world scenario or the current configuration, we are going to obtain the same results, okay? So I'm not going to enter in details, but those who are interested with like business understanding of cybersecurity, you can go through this lab in details, which may take you 90 minutes. And the first step, like we always did, is to import the data that you need. So the first step is to import, the libraries that you need, because if you are working with Python, you cannot access some functions or some functionalities, except if you are calling that from a library that you are importing. If you are importing libraries, you must make sure that you are installing all of them. So in general, if you may find some problems while importing one of the data sets, you need just to go run pip install that data set, okay? Library, excuse me. The thing next that you need to read the data set. So whatever the context, these are your steps. You import the libraries that you need, you read your data set, and in this case, you are going, like we discussed last time, to use pandas, which is the library necessary for uploading or for reading your data, processing it, and visualizing things. You can do that also with matplot to plot distribution or matrices or things like this. And also for Seaborn, it's also designed for visualizing important analysis or features given your data. Now we are calling from pandas, which is called as pdhair, the read CSV file, which is going to read this data, given in consideration that the extension of this data is a CSV file. So now if I'm giving you in the project a data set, you need to make sure what extension is your data. Okay, so, and then based on the extension, you are going to choose the function that is going to read that data, okay? Next, so just we are going to see the columns, the head, the tail, like details about this data set, the shape. So you can see here, the data set is containing like almost 500,000 samples. More information about this, like elements or data, the description, which gives you the number of samples, the mean, minimum value, maximum value, distribution, and so on. The counts for each of the classes, how many, so you can see here it's unbalanced. Next, so you have more like examples, the sum of some columns. You have like, what you are doing here is just you are going through the data set as it is, just a description to see and visualize. You are not solving any problems, you are not doing anything. So next, you need to visualize things in a more clear way, which is to have plots, which is extremely important in data analysis, in AI, to understand things. So here, for example, you plot things to visualize histograms. For example, you can plot like we seen last time. This is another histogram, is given labels. So you can see some labels are not having many samples. Some other labels are having like almost here like 90K samples. So it's showing the imbalance in data. The count of values, which is already plotted there in the histogram. You can also see or discover your data deeply. So you start checking a given component, like for example here somehow there is protocol type, so you can dive into more details and keep checking for that details what you have. Okay, so all this is possible and depends on the data. So it depends on the data what you can see, but these are examples. You can also visualize correlation between the elements in your data set, which is similar, like here duration, you can see one here, for example, source bytes here source bias. So you can see 1. If you keep doing this, so you keep seeing 1 in the diagonal, something similar to the confusion matrix that we discussed last time, which is going to show you the correlation between classes. Now, given this confusion matrix, you can see sometimes some classes are not correlated at all, means there is no relationship between them. You can like figure out or turn out this data into like some insights, and based on that, you can decide whether to drop, whether to strengthen like the weight or the importance of some features. So here we are dropping some columns given the dataset after identifying strong correlations. And next, this is the describe after doing this pre-processing step. You can also deal with the categorical values, which means that you have some types of values and you need, for example, first thing to check how many, like you have, for example, service, how many, flag, how many, protocol type, how many. This all is given the context of this data. And next, like to plot information, to drop some elements, like here we are dropping service element. So this all is pre-processing step and visualization step. Next, we have the feature scaling is an important like step before like feeding your data into ML model, or in particular the KNN. KNN is going to measure this distance. And if we are talking about distance, sometimes your data is not normalized. When we talk about a normalized value, we mean that this value is between, for example, 0 and 1. Sometimes you have data given, for example, image data. You can have your data between 0 and 255. If you are going to normalize, you're going to divide by 255, which is the maximum value. And like this, all your like points are going to be this between 0 and 1. Once you are scaling, next you can apply this type of algorithm, which is working mainly on quantitative values or scalars. So now we need to, before that, also to deal with labels, because if you have labels and you are printing or checking their type, so sometimes the type of the label, it's not like accurate for classification. Here, what we need to encode labels. So they are encoding a label, they are calling the label encoder. And next, what we did, so we are done. Everything is clear for labels. Everything is clear for scaling or how your data is encoded. Now we need to identify if there are outliers, because we know, and it's clear that for KNN, for example, is extremely sensitive to outliers. Sometimes you don't do this, don't check this point, and at the end, you are not finding the expected accuracy or performance of your model. You need to check. So if there are outliers, you are aware. And if there is a way also to deal with that, you can do that. So here we are trying to check that thanks to this box plotting plots. And next we are splitting the data, which this point we were discussing last time. If you are having a machine learning algorithm or a deep learning algorithm, so here we are based on learning, machine learning, deep learning. The word learning is the key for everything. So learning is coming. We are moving from AI, where we were discussing rules and everything is hard coded. Now there is the learning phase, which comes from data. So if you have your data, it's a whole single data set. You need to split it into train and validation. So last time we seen that within sklearn here, you have train, test, split function. And this function takes your whole data set of X's, which means samples, their labels, and you need to set your size, the test size. So here we are dividing or splitting this data into 20% test data, and the rest, which is 80% training data, which is going to be X train for the samples of train. They are having Y train their labels, X test for the samples of test, and their Y test for their labels, the labels of test. Now what we do is that we are just checking how many and the shape for each of them. The shape is extremely important, especially for some models that we'll see in the future, but for her it's just like monodimensional, so it's not a problem. Now everything is ready to apply KNN. What we will do now in this class, we care about this point, which is mainly one single line of code. This is the KNN algorithm, how you apply. The remaining, what we were just discussing, which really worth more time that I'm just trying to summarize things, it's the work that depends on the context. But for a general view, to apply the KNN algorithm, supposing that everything is okay with your data, you just need to call from sklearn, the same library, the k-neighbors classifier. This is going to execute your algorithm thanks to the function k-neighbors classifier, which takes one parameter in this case, which is how many classes, what is the value of k. So here we are setting this value to 4. You can delete this and set it to 5. You can delete it to set it to 10. You can do empirical study on this k. You can apply some techniques or whatever. And this is what we need to do. Once you are calling your model, which is the KNN model in this case, you need to fit. And we said last time how the process of training a machine learning algorithm. So in the start, we have the model. The model cannot predict anything. Expect we feed it training data, and then we have, let's say, configuration or a convergent model towards predicting in the future. So this is what happens always in the fit function that you will find in whatever algorithm, like for the SVM, for the CNN. You fit your model means you make your model learn given the data, which is the trained data in this case, okay, because it learns from trained data. Next, what you have is to predict and evaluate. So here you are going this model, which is trained, the KNN CLF, you can give it some X data to predict things, and you can hence evaluate the final metric. In this case, we are using the accuracy score. We have seen last time multiple evaluation metrics or measurements. One of them is the accuracy. We have seen also the F1 score. We have seen the ROC curve. We have seen what else? Area under curve, related to the ROC curve, and the recall function. Precision. Okay, so there are many metrics. Most famous is the accuracy. We've seen also its limitations, but still people are using, and we are going to use as well. So what we have here, it's now we need to find the best K. So this is what we keep trying, like I was mentioning last time. Here manually you can change the value of K to change it from 4 to 1, 2, 3, or here you are going just to keep it put it into a loop, and you keep checking each time the value. And now we can find that, okay, the best accuracy was with 99.5% with K is equal to 3. So this you are going to use for your ML project. The only thing is your data or business understanding is going to be a different context. So just try to enjoy with that. Any questions? Any questions?
For our project, I'm assuming we're going to use similar things at least. Is there a certain accuracy we should look for as well?
It depends. So you can use accuracy, and you use F1 score, you use whatever we've seen, and you can say the accuracy is giving always more, or the area under curves over covering more. So this I want to let it for you to explore, but you are going to use all 4 metrics that we are seeing. Yes. Okay. So any other questions? Okay, now we will move to the second part. I hope now things are clear. Okay, the second part is that we are going to see or explore another algorithm, which is the SVM, the support vector machine. And Farah is deciding, she was contacting me, we are preparing something to present. So I will let Farah present this part. Just let me share. So you can bring your laptop, I guess. Go for it, and I'll be with you. Yeah. Oh, so for the first slide, present from here, and then we will be moving for the. Now you can share the screen. Okay. Okay. So she's your instructor today.
So hello everyone. So today we'll be talking about the support vector machine, which is one of the algorithms, supervised algorithms that we are learning about. And first of all, I will begin by a quick presentation of my presentation of the presentation plan, actually. So first of all, we will begin by a quick motivation, then an introduction to SVM. Oh, should I? Yeah, okay. Okay. Then we will be discussing some key concepts, and then we dive into some core concepts and mechanism of the support vector machine. So first of all, I wanted to begin with this illustration. As you can see here, we have the data distribution of these data sets. As we can see, there are some blue points and white points. And the question that comes to our minds here is, how would you classify this data? So if anyone has an idea, how should we classify it, or these two types of data classes or something?
The line between those two classes.
Yeah. So what type of line? Because we can. Okay. So like this, you mean? Can you guess what is the function of this line?
Isn't it just like y equals mx plus b?
Yeah. Great, that's it. So it's a linear classifier here, but the problem here is with the W and B. We can have multiple type of lines. So this is the first one, or we can have a line like this, or another one like this, but we have to choose. So if we still guessing which line it is, we will have some multiple choices, but any of these would be fine, but which is the best? And here is the more interesting question. And here comes the concept of margin that we will define, that we will be defining now, which the margin define of a linear classifier is the width that the boundary could be increased by before hitting a data point. As you can see in here, this line can have a variable width, but the margin is when you hit one of the data points in the both sides, and we can see the maximum margin here when we hit the data points of the both sides. And here is the the simplest kind of SVM, which is called the linear SVM. So from here, we will move to the, okay, and SVM stands for support vector machine. And the support vectors are the data points that that pushes up against the margin, as we can see here, in the green color. And from here, we can go to a quick introduction to the support vector machines. It was introduced firstly with Vapnik, which is a Russian researcher in the 1990s. At that time, there was a growing need of a machine learning model that could handle classification in complex and high dimensional spaces. By the way, this classifier can classify even for multi-classes, not just the binary classification or whatever. And Vapnik and its colleagues aim to build that model that both is computationally efficient and theoretically grounded and that find optimal solution to some classification problems. And the main key innovation was in maximizing the margin. As I said, the margin is the distance between the classes, which helps the model to generalize better to new data. And that's what we aim by building these classification models, is to generalize to the unseen dataset. So some key concepts, like we can see here, we can have a line or hyperline based on the dimension that we are talking about. If we are in the 2D dimension, so we will have a line that separates between the two classes. And the margin is the distance, like I said, between the two closest data points from each class, from each side, like we can see here for the orange point and the blue points. And the support vector are the data points that are closest to the hyperplane or plane and play a critical role in defining its position. Okay, so if we are below or if we are in a dimension higher than 2D, the line becomes a hyperplane. That's what means hyperplane. And for the support vector machines, we have two types of this algorithm. We have the linear SVM and the non-linear SVM. As you can see here, and this depends on the types of data that we have. If we have, in the first example, a linear distribution of data points, we can use just a line, which is a linear SVM. If we are dealing, like in the second plot, with data points that we cannot classify just using a line, so we are talking about a non-linear SVM. So the question that comes here is how do we represent this mathematically? So we will begin by the linear SVM. As you said, Zoya, we have our main function is w multiplied by x plus b equals to 0, which is the linear function. And SVM here aims to create the largest possible margin. And by creating the largest possible margin, we are aiming to divide the space, or to classify, to separate the space by increasing the width, like separating very well the classes, so to generalize well after that. And mathematically, this means minimizing the size of W. W is the vector here. If we can visualize it with this figure, it will be the vector that is perpendicular on the line that separates the two classes. So as you can see in blue and red here visualization, we have the minus plane and the plus plane, and the classifier boundary. The boundary will be always in the middle. If we are aiming to classify we suppose that we have a class A is +1. So if we have a point that belongs to the class +1, well, our formula will be w multiplied by x plus b equals to 1. Otherwise, it will be the other situation that it will be equal to -1. And moving now to the nonlinear SVM. So this is when we have the dataset is not linearly separable. So we use a trick to make it work. The first step is to map to a higher dimension. As you can see in the first figure, if we have this distribution of data points in the red and green points, we cannot just separate using a line. So we will increase the dimension to have it like this. As a result, we apply just a kernel and then separate it using a hyperplane, not just a line. So, and when using this kernel, there is a kernel trick. So instead of actually transforming each data point, we use kernel function to calculate distance between points and where they are belonging in a higher dimension. And some of the very common kernels are the polynomial kernel and the radial basis function kernel. We have two plots. The first one is the polynomial kernel. So if we have like in the blue and red points, we cannot separate it by a linear line. Just we will apply the polynomial kernel to make it visually acceptable to separate it just via a hyperplane or a plane. And in the last figure, we have the RBF kernel, which is very similar to the Gaussian kernel, applied in order to move to a higher dimension and to separate our data. And now we move to a summary. So as we did with the other algorithm, our objective from this algorithm is to find an optimal separating hyperplane or line by maximizing the margin or the distance between classes. This algorithm consists of 5 main steps. First of all, we will initialize. What means by initialize is that we will select the kernel based on the data and problem. Then if we are in the nonlinear case, we will be mapping the data to a higher dimension. Then we will be optimizing the hyperplane. After that, we will identify the support vectors, which are the points that are just on the hyperplane. Then we will classify the new data. And finally, here are some advantages and disadvantages of this SVM algorithm. So first of all, it's simple to understand and implement. It's effective in high dimensional spaces, robust for marginal based classification, and memory efficient. Some of its disadvantages is that choosing the kernel can be very challenging, and it's not ideal for large data sets. As any machine learning algorithm, it's very efficient with the small data sets, but if we are going to extend it to a larger data sets, it will not be work as good as we are hoping. And that's all. Thank you. And if we have any question, just let me know.
I have a quick question. So I was wondering about the support vectors. Is that a hyperparameter? Like, can you choose how many you're going to use? Or is it just, you know?
The hyperparameters to this algorithm, you mean?
Yeah.
Yeah, it would be basically the kernel, I think. If we are choosing the kernel, we can just choose if it is linear RBF or the polynomial kernel, and that's it, the hyperparameters.
Gotcha.
Other than that, it's by default. Okay.
Is she answering your question, Zoya?
I think so. My main question was just like, she was saying that they're not hyperparameters. I was just wondering, how do you know how many support vectors you have?
How many support vectors? The support vectors are the points that are near to the...
We can come back to the main picture where we are talking about the support vector. So here, if you are having...
It's based on the case. If you are having here the nearest key point to the I think the line will be this support vector. If
You can show here. Yeah.
Okay. If we suppose that we don't have this point in here, so our support vectors will be just this and this. So basically, they are the nearest points to the line that separates between the two classes. So we will not fix it by ourselves. So it
Here we have to, because what we have we have two like classes. You have the blue class and the white class. So if you have the white class, here we are having 2 points that are near to this line. And these 2 points, they are called support vectors. So in this case, they are giving us the support vectors because the support vector is defined using these data points where the margin pushes against. So here you have 2 points that are defining this one, the mean margin, and one data points which is defining this one. So in this case, you have 1 from this side and 2 from this side. It's only because you are having a binary classification, okay? So you keep doing this in the case of multi-class, but in the case of binary classification, the answer for your question is you have to. One is coming from these points, data points, which are pushing the margin like against, and this one which is pushing from this side. So are we answering your question?
Yeah, that makes sense. Thank you.
Okay. Now let's move with more illustration. I think it will be more clear.
Okay.
You can now join with the. Let me stop presenting from this laptop. Sit down, wait, it's more easy.
Should I join the meeting?
Yeah, sure.
Great presentation, by the way.
Thank you.
Okay. Any other questions? Okay, so I think many points will be more clear now if we are going to go through the lab together. No. I think you can join and then close.
Recording in progress.
Step one from the first one. Okay, so you can see, guys.
Okay, so to illustrate more our um,
So here what we are doing is that we are applying the SVM, which is our third or fourth machine learning algorithm, in the case of neuroscience. So it's not cybersecurity, it's not so we have it in a different use case. The first step is always like we usually did, which is
importing data, libraries and data.
libraries, data, and so on. So sometimes here, if you come back to the data, what is it? No,
Breast cancer.
hey, from data sets. And
Yeah.
if you go up to
It's
the imports, yes,
predefined data sets.
you can show us that line selected. So here we mentioned the difference compared to the previous labs. So in previous labs, I usually shared with you a CSV file, you download that, and then you upload from your computer. Now this time what we will do is that the dataset is already there in some library, which is sklearn, within the set of datasets, and then when you are reading, you can read it from there. Okay?
Yeah. So and here we are importing the data. After that, we are accessing the features which are data, and then the targets which are our classes. Here
So
is
from the name of the data, what we can deduct first thing? You need to read the name of the data.
breast cancer. Which is we are loading the breast cancer dataset and classifying it if it is breast cancer or not.
Okay.
Okay, so the features are here. From this table, we can see the features that we are relying on in order to classify our samples that we have in the dataset. As you can see here, we have two targets, so it's binary classification. If it is 1, it's a cancer. If it's 0, it's not.
So it's not the balanced data set, right?
It's not balanced.
Okay.
Because we have in the malignant like cases are more than the benign ones.
Yeah.
So okay. After that, what we will be doing, we will be standardizing our data set. Then we will transform it, fit transform it to the train and to the train data set. Then we will subplot it to see.
The main objective here is to visualize your data in the 2D space.
To this space.
Okay,
Yeah.
great.
So if we can see here, as you can see, we have multiple data points that I think there are some outliers here. We cannot just separate it by a line. It will not be that accurate.
So you see the human expertise here? She's saying, she's detecting, and she's saying we cannot. So this is when you are understanding your algorithm, you say we cannot. Okay? Otherwise, during the code, you can give the try, you can confirm that what you are saying right now is correct assumption. Okay, great.
Yeah, so and here we can see the distribution of our features, like in here, the mean radius histogram to the frequency of the mean radius histogram of our features, the mean texture histogram. Here are some informations about our features that we have. Moving now to the SVM implementation. So as Dr. Rania said, the SVM or the KNN or other algorithm can be uploaded or running just from a single line of code. As you can see in here, just we imported from the scikit-learn.svm. Here are the parameters that we have by default for this algorithm. So first of all, we will split our data to test and train data, then scale it. After that, we can see a representation of our data for the train and test data sets. It's not linear, as we said here. We cannot separate it by a line either for the train or the test. Okay, so we will be going from a linear kernel to the other kernels that we have. We began by choosing the linear kernel here, then fitting our model. And the accuracy that we have from here is 86%, which is not that good because we are relying on a linear kernel. And from the dataset that we can see in here, it's not. We don't need that linear. To be more accurate, we need to use a non-linear kernel. Here's
if you apply here the linear one, what happens? What you can see? Okay, we can apply it still. The majority of the data is on the top. The majority of the other data set is down. But the thing is that you can see
some outliers.
The elements that are misplaced, they are not matching well.
Yeah.
These are reducing the final accuracy.
Yeah, I think that's why we have 80% and not 90%. And here we will use all the kernels that we have to finally see what we will have from here to.
So we are comparing here the different kernels that are like hyperparameters for the SVM. So what are these kernels, Farah?
So for the first one, we have the linear kernel. As we said, it's the accuracy, it's 86%, which is not that accurate. After that, we have the polynomial kernel. As you can see, it's better than the linear kernel because it's a non-linear method, but still it's not the best. For the RBF kernel, it's here the excellent one, which the accuracy that we have, it's 99%. And from the visualization, we can see that it separates the classes very well, and the sigmoid kernel is not that good. So if we are gonna choose from these, we will rely on the RBF kernel.
So now, is it clear for you guys, like the difference between these kernels and how to choose and, okay, not how to choose, but at least the difference between kernels? Okay, so how to choose is what we are going to see next.
Okay, so here we will see multiple data sets, because I think to choose which kernel is the best, we need to see multiple data sets, because for each data set we have a kernel that can be best for this specific one, as we can see with the previous one. The RBF was the best. So we are specifying here the predefined datasets, the moons datasets, circles datasets, and the blobs datasets. We'll as well choose the same kernels that we have: the linear, the polynomial kernel, the RBF, and the sigmoid kernel. And finally, we'll see for each dataset what we have. For the first dataset, for the moons dataset, we have RBF is the best.
So when she is saying, Farah, about the moon or circle, she's talking about the distribution of the data. It means how you can see the purple ones, it looks like a moon. The pink one looks like a moon for the first row. For the second one, the distribution is kind of a circle, and within that circle there is another circle. And in the last one, what was that?
Blobs.
So it's blobs. So we can see that they are completely separate. Yeah.
So I think for the first one, the RBF is the best, but still the polynomial kernel is also good, because we have a nonlinear distribution. For the circular distribution, also RBF is perfect. But the polynomial is not that good. We cannot rely on polynomial. It's not. It can't just guess. It's not guessing or making anything. It's so.
So it doesn't help in this particular distribution of the data.
So it's better to use RBF as well. And for the blobs, I think it's I'm gonna opt for the linear kernel, because it's making 100% class accuracy. All of them are making a good accuracy, but I think linear kernel is more efficient in the memory and computational time and everything. So if the linear kernel is doing well, we don't have to go to the nonlinear kernels. And here we have the example, as we said, for the breast cancer. Here's a description for the dataset and so on. And finally, we also make just a small fine-tuning and hyperparameter optimization, and the best set of parameters was the kernel was RBF is the best, and it's given a 90% accuracy. And that's all. I hope you understand the SVM algorithm. Any questions?
Is there ever a scenario where RBF isn't the best one? Because it seemed like that one was just really good at adapting.
Yeah, I think it's good for any example. I think it's the best, but it's not in the computational, and for the resources, it's so expensive. So if we have a good result using other kernels, we go for it.
So for the RBF kernel, it is also based on polynomial kernel. If you go back to the mathematical background, that's how it is. So it's kind of multiple polynomial kernels forming the RBF, which makes you, if you are making comparison between these two, which both of them are in the set of nonlinear kernels, So here you may opt for the polynomial one because it's less complex and all. However, if you are thinking of performance, of solving a particular task, or you are having a particular setting and distribution for your data, RBF is good. But what I want to mention here is that even that RBF might be good for all cases, giving the maximum accuracy. However, if I can see from my data, I can linearly separate it, there is no need to move for the polynomial or RBF or sigmoid or these complex, I would say. They are non-linear, which is making them maybe complex. It's better to solve this problem with the easy way, which is the linear kernel, which is at given settings can give you the 100% you are looking for.
Yeah. Okay. So that's all.
Yes, Zoya?
Yeah, that makes sense. Thank you.
Okay, any other questions from others? Okay, so I believe it's clear. I'm sharing, or I'll share this slides and also the notebook with you. So this may help you for the preparation of your ML project. And next time, what we are going to do is you guys start working on your ML project, deep learning project. And for us, we will just finish with the random forest and decision trees for the next time. And we will discuss about the exam. I will for sure give you time. This time it will not be hard because I'm discovering that last exam might be a little bit hard. I was not thinking. The problem with last exam is they're relying for 100, I won't say 100% for all of the students, but relying on ChatGPT was not a good point for many examples. So this time I will make it more simple, so don't worry about that. Okay, if there is no questions, I believe so today we are finishing. We are done. Okay?
Okay.
Okay, see you next time.